what we're recording.
Okay, so for the people in the room, that was a slightly longer than expected break due to the inadequacies of the recording equipment. For the people at home, well, you just clicked on the next link on YouTube, didn't you? So that's fine. So where we got up to before the break was we showed how you can do the change of coordinates from a random element somewhere in your mesh back to the reference element. And we showed that you could actually do that for a coordinate field representation that was linear or any other set of basis functions that we wanted to have. So now we're going to go back to what we were doing earlier and actually then do the integral. So what this means is that we have the integral over the reference element. I realized in the first half of this lecture I was inconsistent about whether I was calling the reference element T0 or E. Let's just try and stick with T0 for the rest of the lecture. Of the function 1 times the Jacobian, or the determinant of the Jacobian, dx. And so what we're going to do is we're going to approximate that integral using quadrature. So that means that we say that that thing is approximately equal to, so if you use enough quadrature points, so if you're, that's a polynomial, right? So if I had polynomial basis functions, then their derivatives are still polynomial, and so when I start multiplying them together and get terms, actually that's not quite true. If we're affine, then that's constant and we're fine. For higher degree, then we get into trouble that you can't actually exactly approximate that with polynomials. But we'll approximate with polynomials, and we'll assume that we used enough that the approximation error is not a big deal. So that's equal to sum over, so I'm going to use GI for the quadrature points because that's what's in fluidity. G I think stands for Gaussian in that case. Times 1, which I can evaluate wherever I like because it's a fairly simple function, times the determinant of J, and that has to be evaluated at xgi. Right, because now J, so in terms of what we did earlier, this bit is the integrand. So J is part of the integrand, so if I'm going to approximate the integral using quadrature, then J is one of the things that I have to evaluate at the quadrature points. And that is then multiplied by the corresponding quadrature weight. And so now in order to evaluate this integral now, so that's a sum, and unless you're a particularly slow first-year computing students, you know how to evaluate a sum by writing a loop. And so the only thing we now need to do is to evaluate that thing. And so we know how to evaluate the determinant of a matrix once we've got the matrix, so that's easy. And so we just need to get the Jacobian out. And as we noticed before the break, the Jacobian is equal to the x gamma dx tau, which is equal to the sum over I of x I d phi I evaluated at the current point, which is xgi, the gamma component of that, over by d x gamma. Okay, so where did that get us? So let's just keep a little bit of a track on all of the indices that are in play now, because there's a lot of them. So this is I, this is the sum over the basis functions on my local element. This is GI, this is the quadrature point at which I'm evaluating this. This is gamma. This is the component of the position that I'm taking the derivative of. So this is the derivative of x with respect to whatever, or y with respect to, that's controlled by this.
Should be tau.
And this is which direction, which local direction. So local direction 0 or 1 or 2, I'm taking the derivative with respect to. So where did this come from? So if we're going to write some software for implementing this, so we write a piece of software, which those who work on my project will call a kernel, for evaluating this integral on one element. So we have to ask, what information do we need to pass into that one element? Well, what are the things that we don't know in here? So that, given that when we wrote down, or respectively generated using form compiler, the quadrature rule, that's static data, so that's just sitting in the kernel, written down as a literal constant probably. It's certainly a static of some sort. And this thing, this is different on every element, right? This is the vector of coordinates of the nodes of the coordinate field. So this thing, that's input. And now I need to do this guy. So this is a basis function, which I can write down as a polynomial. But the important point here is, given that I worked out, when I wrote down this kernel, what the quadrature rule was, that means that when I wrote down the kernel, I chose all of the points that I was ever going to evaluate these guys at. So that means what you do is, offline statically, you work out a matrix, and that matrix, which we might call d phi, d phi has indices I, gi, gamma, is tau. And d phi I, gi, gamma, tau contains the value d phi I, x, gi, gamma, dx, tau. Right, so now I've nailed down all of the indices that occur in there. And that's static data. For big elements, that's quite big. So for high order elements in more dimensions, that can be a lot of static data. For the people who are interested in tensor product elements, there are smarter things that you can do. Right? You could factorize this and store the factors of this matrix. If you did that, you'd store an awful lot less static data. So when people from time to time hear me complain that our implementation of tensor product element is stupid, the sense in which it's stupid is that we don't factorize this. We really do currently write down that whole thing, and that gives you a huge iterations, a huge amount of static data. Yeah?
So in the affine case, this matrix is the same for all elements?
So in the affine case, it's the same for all quadrature points. So in the affine case, that goes away. Right? And in fact, what you can do, what Phoenix and therefore Firedrake currently do, is they have a hard-coded assumption specifically for the Jacobian, that not only do we know that we're in the affine case, so I won't bother to write down d phi and contract it with xi. I will expand that out literally and paste it into the code. That's actually what goes on. But there's no particular reason to do that. You get exactly the same thing by backing out here. So, okay, so that's that. That's how to get an integral. You'll notice that we still haven't actually written out the integral for our Poisson problem that we always like to write out. Fortunately, we have now given ourselves essentially all the tools we need to do it. So now what we're going to do is write out the formula that we got last week for the Poisson operator in more dimensions and change it into local coordinates. So this. So the integral we actually wanted to do was not the integral 1, it was integral over some triangle of grad phi dot grad psi. Oh, whoopsies. It's not psi, that's integral phi. Dx. And now I'm going to be a little bit careful here, and I'm going to put small x's on those grads. Because in terms of what we did last week, what we've actually written there is the best way to write this. So because the definition of grad x phi dot some direction that we wrote down last week, so that's the limit as h goes to 0 of phi of x plus h x tilde minus phi we use epsilons in the paper, but it's the same thing. So that is all defined in terms of small x. Right? That's a gradient on the actual real triangle. So another way of writing this, so we can write this back in the terminology that you might find yourself more familiar with, we could say that this is equal to the integral of the phi I dx dx k d phi j dx k dx. Right, so that's a repeated index here. It's a dot product. You sum over those. But those are gradients with respect to little x, the physical coordinate. So now let's try and turn this into an integral we can actually do on the triangle that we've actually got, which is t0. So this is the integral over t.
That's a psi though, right? Since you
Yeah.
named it.
Because I'm being well behaved. Actually, in the case we were doing last week, they are the same.
The same, yeah.
But,
Oh, because you wrote it.
yeah. So we can, yeah. They don't have to be, right? We can write down this form however we like. So that's equal to the integral on the reference element of the phi I xk, the phi to remember that I changed the expression. J okay. Sorry.
Where's the Jacobian?
Yeah.
Okay, so far so good. And now what's happened? So this is a loop that we're going to do over all the i's and j's in the mesh. Now obviously this loop we only have to do for those phi i's and psi j's which are non-zero in this element. So I j equals 1 to whatever the local basis size is. So if these were both P1 on triangles, that would mean these would be going from 1 to 3 each, right? Whereas up here, these are looping over however many nodes I have in the entire mesh. This is where when we restrict to the local one of the benefits is we get to not look at most of the data. So, what do we now have to do? Well, we've got a bit of a problem. So I know what these are. These are individual local basis functions. I know how to write those down. That's straightforward. These are still derivatives with respect to the original physical coordinate out there on the original element. So actually what I've written down here at the moment doesn't make much sense. Right, so here's my physical coordinate. I know a function here, and somewhere out here is weird elements, and there's my change of coordinates. And this is x and this is x. So I know the function here, but I need its derivative over here. So we need to change coordinates in here. And the way we change coordinates is with our friend the Jacobian. So if we were, let's just go back and pretend that we're in one dimension again, and we can apply the chain rule. So the chain rule would say that the phi I dx is equal to dx dx right? Chain rule. And that's now fine. The reason it's fine is because I know what, I know d little x, d big X, and I know from some undergraduate calculus so I did this before, right? That was just what I did to get with the Jacobian. It's just expressing things in terms of basic functions. If I got that one, I've got that one. So life's good. So how do I write this down then in the more general case where I've got a k here? The answer is I just need all the derivatives. I've committed a horrendous sin here on this board. Bless me, Father, for I have sinned. I have broken my own rules. Those are all little kappas. Right, those are directions.
Can I ask something?
Yeah.
So, the first expression is a loop on all the elements essentially, all the test and the trial basis functions, and then you equal that to something that's a loop on one element.
So this is a loop on one element.
Oh, okay.
It's just that
Okay,
until I restrict myself down here, I don't really have a way of knowing.
So you're saying that that's on one element, but okay, understood.
On this element, right?
Okay, yeah. Okay, understood.
Yeah. So it is sort of. It's actually already true that most of the basis functions here are zero, but I don't really have a convenient and straightforward way of working out which basis functions are zero. So really, at that point, I have to go over all of them. But now that I'm down here, now that I'm on this one, I only have 3, 6, however many basis functions for my current function space on here. And so then I can really restrict it down. I can really write the local operations out. So what I do here is my kappa. So now I need another, so I need to do this for all epsilon, right? So this is, I should use tau here, shouldn't I? Tau. And that's repeated, so that's for all tau, and that's going to be repeated up there, so that's for all k. So what that is, well, if the little x's were on top and the big x's were on the bottom, we'd know what that was, right? If the little x's are on top and the big x's are on the bottom, that's the Jacobian. So it's the inverse Jacobian. So now, this thing here I'm going to, so this thing here, I can now make this very compact by shifting back to vector notation. This is just J inverse grad big X, right, gradient with respect to the local coordinates, phi I, dot J inverse grad big X, not one of those, psi J and now all I need to do is evaluate all of these at the quadrature points and weight them. Right, so this is still an integral. So I approximate that by, oopsies, not equal, the sum over all the quadrature points of J inverse evaluated at the quadrature point, grad X, wrong X, phi I evaluated at the quadrature point. Where? That should be separate. Dot J inverse evaluated at the quadrature point again, grad X psi J evaluated at the quadrature point Right, so that looks really rather complicated. It's not. Because what we've just done is written that whole thing out in terms of numbers that we can pre-compute and the Jacobian, which we know how to compute. So just a bit earlier, we worked out how to get the Jacobian. Having got the Jacobian, we can work out for at any given quadrature point its determinant. We can work out its inverse. Inversing a 1 by 1, 2 by 2, or 3 by 3 matrix is an easy thing to do. Because remember, that's the size of that matrix is just the dimension of the space we're in. It doesn't have anything to do with what basis functions are at. It's just a geometric size. So that's always 1 by 1, 2 by 2, 3 by 3. And now this story is exactly the same That's what we were talking about earlier. So now, what I have to record for phi is I need to have, well, I did it before, d phi has, and I'm going to get this confusingly wrong because I'm going to manage to put the indices in a different order, but I, G, I, tau, gamma, gamma tau, sorry. And that is just d phi at xgi, phi I at xgi, gamma dx tau. So that's static data. That's in fact exactly the same static data we had earlier. And exactly the same thing's going to happen for psi, right? Just by symmetry. So I have a deep psi, I, Gi, gamma, tau equals d psi, I, x, Gi, gamma, dx tau. If I had a slightly different form in here, so if I had the right-hand side form where I don't have derivatives, then I'd get to exactly the same point, but I wouldn't have any gradients in here. And so then the static data I would need would be, say, phi of I, Gi, and that would just be the basis function phi I evaluated at Gi of this still potentially a gamma, right? This is a vector valued function, a vector valued basis function, so I need to store the component of the basis function at that point. Because we're a scalar valued basis function, aren't we? And in fact, in this case, this is a scalar valued basis function, so that's a slightly different case. Right, so in this case, actually, yeah, so I just misled you. These are scalar valued, so here we only have the simpler case. Right. So you only get this extra gamma in here if you have a vector value basis function. Okay, so we are just about out of time there. So we took one lecture to power through how to write down the integrals in terms of the quadrature. But that gets us a long way, right? So knowing that, you can actually write a finite element system. You know that that's the information you need to write down. That's what it takes to actually do it. And so I think what we're going to do next week is I think we're going to look at what you have to do if your system is nonlinear. And that's interesting to solve nonlinear systems, but the other real reason I'm doing it is because if you understand how we solve nonlinear systems, then that also gives you an insight into how we impose boundary conditions. So that's what we're going to do that.
Last line soon.